Hello everyone, this is your captain speaking. First, I would like to welcome you all aboard as we are about to explore the concept of wing structure and configuration. Fasten your seatbelt and let's get started.
The wings are airfoils attached to each side of the fuselage and are the main lifting surfaces that support the airplane flight. Aircraft wing design is different according to flight characteristics and conditions. The particular design of a wing depends on many factors such as the size, weight, speed, rate of climb, and use of the aircrafts.
Wing configurations vary to provide different flight characteristics. The amount of lift aircraft generates, control at different operating speeds, stability and balance all changes as the aircraft wing shapes is changed.
There are three types of wing configuration that we have to consider, namely based on shape, based on position, and based on support. To further understand this, we will discuss this one by one as we go on.
Let's go!
Let's go!
Let's go!
Let's go! Aircraft wings are airfoils that create lifts when moved rapidly through the air. Aircraft designers have created a variety of wings with different aerodynamic properties. Attached to the body of an aircraft, let us discuss first the wing configuration of aircrafts based on shapes. So first, the rectangular wing. The rectangular wing is the simplest to manufacture. It is non-tapered, straight wing that is mostly used in small aircrafts. The wing extends out from the aircraft's fuselage at right angles approximately. So the rectangular wing is similar in efficiency to the elliptical wing, but it is much easier to build. Rectangular wings have very gentle stall characteristics with a warning buffet prior to stall and are easier to manufacture than elliptical wings. So one drawback to this wing design is the rectangular wings that create more induced drag than an elliptical wing of comparable size. So isang magandang example ng aircraft where rectangular shape is used is that kagaya nung pinakitang picture sa gilid, which is the Piper PA-38. And one major disadvantage of a rectangular wing is that it is not aerodynamically efficient. So next is the elliptical wing. So the elliptical wing is aerodynamically most efficient because elliptical span-wise lift distribution induces the lowest possible drag. However, the manufacturability of this aircraft is poor. So an elliptical wing is a wing planform shape that minimizes induced drag. This shape shortens the chord near the wingtips in such a way that all parts of the wing experiences equivalent downwash and lift at the wingtips is essentially zero, improving aerodynamic efficiency. So, however, this wing design is difficult and costly to manufacture because of the compound curves in its design. So, third is the tapered wing. So, the tapered wing was designed by modifying the rectangular wing. The chord of the wing is varied across the span for approximate elliptical lift distribution. So, the tapered wing is the planform found most frequently on gliders. So, assuming equal wing area, the tapered wing produces less drag than the rectangular wing because there is less area at the tip of the tapered wing. So, if the speed is the primary consideration, a tapered wing is more desirable than a rectangular wing, but a tapered with no twist, also called as washout, has undesirable stall characteristics. While it is not efficient as the standard elliptical wing, it does offer a compromise between efficiency and manufacturability. So next is the reverse tapered wing. So the reverse tapered wing have a more improved cross-sectional area distribution and it is suitable for an aircraft with smaller fuselage but it may cause weight penalty. So this is just basically a planform configuration in which the chord of the wing of an airplane increases with distance outboard from the root. So this is an attempt to address the pitch up problems, which is actually due to the thrust with aircrafts traveling at a high speed. So next is the delta wing. So this low aspect ratio wing is used in supersonic aircrafts. So the main advantage of a delta wing is that it is efficient in all regimes such as subsonic, transonic, and supersonic, wherein subsonic means flight through low speed flows, transonic means flight closer to speed of sound, and supersonic flows means flight through high speed flows, wherein the delta wing doesn't just offer efficient flight experience, but it is also strong structurally and provides large volume for fuel storage. So this is also simple to manufacture and maintain. However, kagaya ng mga ibang aircraft, meron siyang mga disadvantages, and this includes the following. So dahil nga low aspect ratio sila, so delta wings produce higher induced drag, and at a low speed during landing and takeoff, these wings have a high angle of attack mainly because at such low speeds, vortices generate lift, and high stall angles of the delta wings compensate for this. And lastly, the swept back wing. So the aircraft wings whose leading edges are swept back are called swept back wings. So swept back wings reduce drag when an aircraft is flying at transonic speeds, meaning flying closer to the speed of the sound. So majority of high-speed commercial aircrafts uses swept back wings. It is just because it reduces turbulence, wherein during flight, airplanes encounter turbulence from the friction created as air runs through the plane's wings. So the speed at which an airplane flies will affect the amount of turbulence it encounters. So at faster speeds, airplanes encounter more turbulence due to the increased friction of the air running across its wings. So in some cases, the air can travel faster than the speed of sound, resulting in heavily turbulence that is not only a nuisance for passengers but also a danger to the aircraft's structural integrity.
Good day guys! Today we are going to talk about wing positions. Wings can be mounted on the different area on the fuselage. So continue watching to find out the different wing positions and their features. First is the high wing. The wings in the high wing is located on the upper part of the fuselage. In having a high wing, your advantages will be you will have a clear view of the ground. Plus, the gravity will help the fuel flow from the fuel tank to the engine without a fuel pump. It is also inherently stable since the center of mass is situated below the center of lift. Some of its disadvantages are restricted visibility of the aircraft above you. You'll be needing a ladder when refueling or when inspecting the fuel tank. It will be heavier because you will have a separate strut from the landing gear. Next is the low wing. In low wing, the wing is located on the lower part of the fuselage. Your advantages in having a low wing is your fuel tank is easier to reach during refueling and during inspection. It will also have a better overhead view, while your disadvantages are the wing will block the pilot view of the ground. Plus, you'll be needing a fuel pump so that the fuel can reach the engine, since the fuel tank is located on the wing. The third wing position is the mid-wing. From the word itself, the wing is located on the middle part of the fuselage. Some of its advantages are least amount of interference drag. Plus, it leaves more space for wing-mounted ordnance and engine. While its disadvantages are, it will become heavier if the landing gear is located on the wings compared to the low wing. It also needs to pass through the fuselage, or it should be strengthened around the fuselage but it will only cause weight penalty. The fourth wing position is the parasol wing. The parasol wing is located above the fuselage, so it is connected by a cabin strut or a pylon strut. Its advantages are also the same with the high wing. You will have a clear view of the ground. Same as true with the disadvantages. You will have a heavier weight because of the extra part that will be needed to connect the wings to the fuselage, which is the cabin. The fifth wing position is the gull wing. It is also called the Pulaski wing. It has a bend in the wing inner section towards the wing root. It is made to produce a clearance for the engine mounted on the wings, with the wing box still located on the lower part of the fuselage. The next wing position is the dihedral wing. In the dihedral wing, the wing tip is higher than the wing root. Having a dihedral wing can help you achieve more lateral stability, but remember, too much lateral stability can cause your aircraft to do a Dutch roll. And the last wing position is the anhedral wing. In anhedral wing, the wing tip is lower than the wing root. Anhedral wing is basically the negative dihedral wing. Having an anhedral wing will help you induce roll instability and will improve your roll maneuverability. So that's all for the discussion of the different wing position. For the next topic, my groupmate Kevin Libara will discuss to you about wing support.
Thank you for that, Mr. Sawi. We are done with the report of the wings based on its shape and based on its position. And now I am here to report all about the wings based on its support. The wings of an aircraft are designed to lift it into the air. The particular design for any given aircraft depends on a number of factors such as size, weight, use of the aircraft, desired speed in flight and at landing, and desired speed of climb or rate of climb. The wings of aircraft are designated left and right, corresponding to the left and right sides of the operator when seated in the cockpit. We have two types or kinds of wings based on support: the cantilevered wing and semi-cantilevered wing. Cantilevered wing looks like this one. It has no external struts or bracings. All support is obtained from the wing itself, while the semi-cantilevered wing looks like this one. It has wires or struts to support the wing. Here is a side-by-side comparison, of course. This being the cantilevered wing does not have any external struts, and this being the semi-cantilevered wing having external struts. Here is the cantilevered wing. There are no external struts coming from the fuselage connected to the wing itself, while the semi-cantilevered wing has external struts connected from the fuselage to the wing itself. Often wings are full of cantilever design. This means that they are built so that no external bracing is needed. They are supported internally by structural members assisted by the skin of the aircraft. Other aircraft wings use external struts or wires to assist in supporting the wing and carrying the aerodynamic and landing loads. Wing support cables and struts are generally made from steel. Many struts and their attached fittings have fairings to reduce drag. Short, nearly vertical supports called jury struts are found on struts that attach to the wing a great distance from the fuselage. This serves to subdue strut movement and oscillation caused by the air flowing around the strut in flight. So once again, this is a cantilevered wing and this is a semi-cantilever wing. Cantilever wing has no external struts or bracings and all support is obtained from the wing itself, while semi-cantilever wing have wires or struts to support the wing. That's all for the wing based on its support, and now we have wing construction to be reported by Ms. Rain Masad.
Let us now move to the wing construction. Wing construction is almost similar amongst modern aircraft. In simplest form, in the internal framework of most wing, it is made up of spars and stringers running spanwise and ribs and bulkheads or formers running chordwise. The main objective of wing internal structure is to withstand the bending and shearing forces that is act upon the wing during flights. In assent with that, spar is a main structural member of the wing that holds or supports the distributed loads and as well as the concentrated weight such as fuselage, engine, and landing gears. The skin where the wing structure are attached also transfer the loads or the stresses to the wing ribs. The ribs in turn also transfer the loads or stresses into the wing spars. In general, there are three fundamental designs in wing construction, specifically multispar, monospar, and boxbend. Starting with the monospar, what is remarkable about it is that it only assimilates one spanwise or longitudinal member in its construction. Ribs and bulkheads are used to get the required wing shape. In addition, there is what we call the strict monospar, where there is the integration of the false spar in the trailing edge as a support to the control surfaces. The next one is the multispar. From the word multi, it consists more than one spanwise or longitudinal member in its construction. Just like the monospar, the bounding shape of an airfoil uses ribs and bulkhead to satisfy the required wing shape. And lastly, the backbend. Keep in mind that in the backbend, it uses two longitudinal members with connecting bulkhead to get the shape of the wings. The ribs give its wing its cambered shape and transport the loads or stresses to the skin and stringers and to the spars. Ribs are also used in ailerons, rudders, and stabilizers. Aside from the different design, we also have to consider the primary structures of the wings, which are wing spars, wing ribs, and wing skin. Let us start with the wing spars. The wing spars are the primary structural components in an aircraft wing. They are placed parallel to the lateral axis from the fuselage to the wingtip. Basically, the shear loads of the wings are carried by the wing spars. Depending on the design criteria, they are made up of wood, metal, or any other composite materials. At this phase of change, wing spars are made up of solid extruded aluminum or aluminum extrusion reverted from the spars. The next one is the wing ribs. The wing ribs are the structural components that are used in making the framework of an aircraft wing. Mainly, they are placed on the leading edge and the trailing edge component. Ribs give shapes to the wing and it acts as an intermediate component in transferring the loads to the spars and stringers and as well as the overall loads on the aircraft structure. Last but not the least is the wing skin. Wings are designed to carry some parts of the flight and grounded loads with combining spars and ribs. This type of skin is called as the stress skin design. Basically, wing skin carries the bending moment. The lower covering is designed to carry tension forces, whereas the upper covering is designed to withstand the compression forces in order to avoid buckling. That ends our discussion with regards to wing structure and configuration. Thank you for listening.
Thank you for listening. The response to Think About Things has been overwhelming. Stay healthy, stay fabulous. You guys are beautiful. Never forget that.